Okay, so we're going into Module 3, and we're going to start talking about resistors in series and in parallel. So this is going to be our prelude to going into simplification of circuits with expansion as a way of seeing voltages and currents and how they progress through a circuit. So let's start by seeing how resistors combine in parallel, or excuse me, in series. So resistors in series. Okay, so we're going to start with we're going to start deriving this basically with a circuit that consists of an independent voltage source and N resistors all connected in series. Okay, so this voltage source we'll call V sub S. This is R1, R2, all the way out to the nth resistor. N can be 3, it could be 300 million, it really doesn't matter. All right, because this is a series circuit, do this in red, because this is a series circuit, there's one current flowing through each one of these elements, okay? And I'm going to label that current right here, and I'm going to call it I sub S, okay? IS is the current that flows through each element. It's got to flow from minus to plus through the source, so it can, so then it will flow through the resistors by going in a clockwise fashion here. There's only one source in the circuit. It has to be delivering power, so the current's got to flow from minus to plus. So as a result, when the current flows through each one of these resistors, it'll create a voltage drop with this polarity such that the passive sign convention will hold. I'm going to call that V1, this one V2, all the way out to V sub N, the nth voltage drop across the nth resistor. Okay, so now we are going to write a KVL equation around this loop. Okay, so by KVL, starting with the voltage source here, moving from minus to plus, I'll add VS. Coming around to the resistors, I'm going to move from plus to minus through each one of the resistors. So I will always be subtracting the voltage, so it'll be minus V1, minus V2, all the way out to minus V sub N, and that's going to sum to 0. Okay, so now I'm going to leave VS on the left-hand side and move V1 over to, and V2 all the way to V sub N out onto the right-hand side. So now I'll have V sub S is equal to V1 plus V2 plus dot 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 plus V sub N. Okay, so now we know by Ohm's law that V1 is equal to IS times R1, V2 is equal to IS times R2, all the way down to V sub N is equal to IS times R sub N. And so we're going to substitute all of these Ohm's law equations into the right-hand side of the expression here. So we'll have V sub S is equal to I sub S times R1 plus I sub S times R2 plus dot 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 all the way out to I sub S R sub N. Okay, on the right hand side I've got this common I sub S term which I'm going to pull out in front. So I'll have V sub S is equal to I sub S times R1 plus R2 all the way out to R sub N. Okay, now this looks very much like Ohm's law, right? It looks like V is equal to I times R, where R is now the sum of all the resistors connected in series. All right, so what we say here is that resistors in series combine by adding. So we can write V sub S is equal to I sub S times R1 plus, well, hold on, let me do this a little bit differently. I sub S times REQ, where REQ is equal to R1 plus R2 all the way out to R sub N. Okay, so resistors in series combined by adding, very simple. All right, so if we were to look at a kind of a trivial example, a very simple example, let's go back. Let's do something else first before we do that. So coming back up here, here's this circuit in series of all these resistors. We can actually just redraw that circuit as a single voltage source, just like before, V sub S, in series with a single resistor, REQ. I sub S is still the current flowing through the circuit, but now we just have this equivalent resistance for all that represents all the series resistors. Now let's do an example with some real numbers. So let's say we have a circuit with a couple of series resistors in it. Okay, so let's say this is our circuit. So we have an 8-volt source, a 10 ohm resistor, and a 6 ohm resistor. And we have this current here, I, that we need to solve for. So we'll have that, we can simplify the circuit down to a single source. And a single resistor. The single resistance is 16, which is equal to that 10 plus 6 series combination. Okay. And we have the current I, and this is just an Ohm's law equation now. I is equal to 8 over 16, which is equal to half an amp. Okay, so resistors combine by adding. Simple as that. All right, so let's look at resistors in parallel. Okay, resistors in parallel are a little bit more complicated, but we're going to derive them in a very analogous fashion to how we did series connected resistors. So I'm going to, the circuit we're going to use to derive the behavior consists now of an independent current source and N resistors connected in parallel with that source. So we have a current source I sub S, we have resistor R1, R2, all the way out to R sub N. Okay, because everything is connected in parallel, they will have the same voltage. Remember, there's only 2 nodes here. There's a node here at the top, and there's a node here at the bottom. All right, so there'll be 1 voltage. I'm going to label that voltage and call it V sub S. Okay, I've labeled it such that the current source is delivering power. The current is flowing from minus to plus with respect to that voltage. It's the only source in the circuit. It has to deliver power. And so that current now will flow into this top node and divide, and we'll get I1 flowing into R1. We'll label I2 flowing into R2, and we'll label I sub S flowing in, I sub N, excuse me, flowing into R sub N. Okay, and I'm going to call this node 1 here at the top. So by KCL at node 1. We're going to have, we're going to do currents flowing in equals currents flowing out. So we'll have I sub S is equal to I1 plus I2 plus all the way out to I sub N, just by writing that KCL equation. Oops, sorry. Okay, so I'm going to do just a little bit of switching here. I'm going to put the currents for the resistors on the left-hand side. So I'm going to do I1 plus I2 all the way out to I sub N is equal to I sub S. And now we're going to look at Ohm's law for the resistors. Okay, so V sub S is the voltage drop across each one of these resistors. So we can write the current expressions for each one of those resistors as I1 is equal to Vs over R1, I2 is equal to Vs over R2, and all the way out to I sub N is equal to V sub S over R sub N. Okay? So we're going to substitute these values, or these Ohm's law equations. We're going to substitute these into the left-hand side of the equation here. So we're going to have Vs over R1 plus Vs over R2 all the way out to Vs over R sub N is equal to I sub S. We've got this Vs common term in the numerator on the left-hand side. So this is going to be Vs times 1 over R1 plus 1 over R2 all the way out to 1 over R sub N is equal to I sub S. So now if we divide this resistor term here over to the right-hand side, we'll have V sub S is equal to I sub S multiplied by 1 over R1 plus 1 over R2 all the way out to 1 over R sub N. This algebra isn't as nice as a series connection, obviously. Okay, so now we can let Vs equal I sub S times Req, where Req is equal to 1 over R1 plus 1 over R2 all the way out to 1 over R sub N. Okay, there isn't a nice easy way to say this, but resistors combine in parallel as the inverse of the sum of the inverses. So the inverse here of the sum of the inverses. So let's write that down in words, although probably won't want to say it very often. So resistors in parallel combine as the inverse of the sum of the inverses. Okay? So let's look at the case of two resistors. So I want to look at Req is equal to 1 over R1 plus 1 over R2. Okay, so if we did some math here, this would equal 1 over, we'll find a common denominator here, and so this will be R2 plus R1. Okay, so now when we do that inverse there, we'll have Req is equal to R1 times R2 over R1 plus R2. So when we're just looking at two resistors in parallel, we combine them as the product over the sum, okay, which is a nicer way to remember these things. Okay, So let's do a very simple example here. We'll have a one amp source, resistors connected in parallel. We'll just do 2. We'll do a 6 ohm and a 3 ohm resistor. And let's say we want to find this voltage here, V, call it Vx. All right, we can find that by simplifying the 2 resistors. So we can redraw this as a single current source and a single resistor in parallel. 1 amp. And this equivalent resistor, Req is equal to, since this is just 2 resistors, it's the product over the sum. So it's the product 6 times 3 over 6 plus 3. So this is 18 over 9, or 2 ohms. And we're still solving for this voltage Vx. Okay, so Vx, by writing Ohm's law, is equal to the current 1 times the resistor 2. Excuse me. And so Vx is equal to 2 volts. Okay, so this is the first lecture. We're going to do some more talking about resistors in series and parallel. We'll do a little bit of kind of summary in the next lecture, and then how we're going to apply this and use this, and what are some of the special cases as well. So that's coming up next.